I think this would be a fun example. This is the example that I mentioned briefly on Wednesday that you really would have a very difficult time, I think, building an iterative solution for. So it's more of an example for which recursion is not just like kind of a fun little programming trick to have added to your bag of tricks that you can take advantage of, but it really enables a type of solution that otherwise really wouldn't be as tenable. So we're going to talk about this, but it's a little abstract, this concept of backtracking. And it's a technique, and typically that one that uses recursive, that builds up partial solutions that get increasingly closer to a goal, usually involving sort of a recursive search through a solution space versus an iterative search through it. The idea is that as you build up a partial solution, you eventually may hit a wall where you cannot go any further and make more progress towards a total solution. And at that point, that's what the backtracking would be doing. We recursively go closer and closer and closer to our final solution until for whatever reason we cannot go any closer, and then we just take a step back. And recursion allows us to do that in a way that which if we were trying to implement that using iteration, using loops, it would be quite a bit more challenging to do, but we go down our recursive call stack until we can go no further, and then due to that nature of recursive calls, when we return back, we leave off where we were before we went to that final n+1 step. So the type of problems would be those for which there can be a partial solution along the way that you can determine whether you can go any further or whether it needs to be abandoned. That's all very abstract. So even as I had that slide together, I realized, well, it only kind of makes sense to me. So I don't know how much it's going to make sense to you. But it's a type of recursive solution where we build up the solution as we go, but we recognize that as part of the solution space, we may have gone too far down one path. We need to go back up and then down a subsequent path along the way. So it's a very famous problem in computer science, the n-queens problem. And it is referring to a chessboard, not necessarily a standard chessboard, although we can certainly solve it for a size n=8 chessboard. So most commonly stated, the n-queens problem is asking how many ways, and not just finding a way, but how many different ways can n queen pieces be placed on an n by n chessboard so that none of the queens have other queens in check. None of the other queens are able to attack or take any of the other queens. Just in case we're not chess experts, and I'm okay with that as well, right? Queen is kind of the most powerful piece, right, in chess, because it can move as far as it wants or as short as it wants, horizontally, vertically, or diagonally. So if you have your queen placed here, these little white dots are kind of indicating all the other spots that the queen could attack if there was some other piece in any of those white spots. So again, the n-queens problem is how can you place, or how many different ways can you place n queens on a chessboard so that nobody can attack anybody else, so that they're all safe, at least for that turn. It's not actual chess, right? Usually chess, there's going to be 2 queens, maybe you promote, get a 3rd or a 4th queen. So it's an abstract problem just using the chess pieces as part of it. I would argue it's a famous computer science problem. I would argue that there's no straightforward, obvious solution, even for pretty small n values. For n=4, I think we can create one. But for n=8, that's just a single queen. Let's try to create one for n=4. Okay, and this is just using like kind of the pen feature, so it's not going to be actual queens being drawn here. I can put a queen here. That's 1 queen. I got to get 4. Where can I place the second one? Yeah, it has to be a knight move, right? Because if I put it here, that's no good because it's horizontal. If I put it here, it's no good. That's diagonal. Make a knight move. What do I do with the next one? I'm already in trouble, right? I've already kind of failed. So we can solve it. We can definitely solve it for n=4. But as part of that backtracking solution, something we will see is we're going to continue. We're going to go either column by column or row by row. It doesn't really matter. And we're going to continue making partial progress towards a solution until we hit a dead end. And at this point, maybe it's obvious, maybe it's not. We're able to place the 1. Of course, it's safe. It's the only one we've placed. We've now placed the second one. It's safe. We actually cannot place a 3rd one because this queen is in check, this queen is in check, this queen is in check, this queen is in check.
I think there is a spot, the top right, another knight from the
Yep. We could place and I've seemingly lost my cursor here. We could place 3 queens. I lost my cursor. Oh, there he is. We could place 1 right here. That's where you're kind of saying, yeah, but placing 3 isn't good enough. We got to place 4, and then we're still stuck. And for at least our recursive, our backtracking solution, what we would do is we would go back a level. We'd say, and I erased it all, we'd say, well, I tried to place 1 here. If I go back to where I was, and we can walk through it this way. We had 1 here. We had 1 here. We can then backtrack and say, well, that didn't work. Now let's see what we can do when we place 1 here. Okay, we place 1 here. Can we place something in the 3rd column now? Yeah, we got our knight move, whatever you want to call it. And then can we place our final one? No. So our backtracking solution fails again, fails not only to place here, fails to place anything in that 2nd column, right? In that 2nd column. So we would have to start over and say, well, our first placement of the first queen is never going to work. In fact, we've actually kind of, in some sense, proven that we can't place a queen in that first position and have 4 queens placed on the board at one given time. So when I say it's not a straightforward, obvious solution, this is all I'm kind of getting at. If we start with the queen here, well, then that helps us know that the only 2nd queen can go right here. That opens up this queen right here. And then we get a queen right there. So we can place our 4 queens in that case. And it turns out for n equals 4, there they are. There's actually just 2. And there's actually only 2 solutions for n equals 4. If you think you have another solution, it's just some sort of rotation or flipping of those 2 solutions. There's only those such 2 solutions. So it's a famous computer science problem. Okay, it's solved for n equals 4. N equals 8. We know the solutions for a reasonable range of n values. But in terms of solving it, I think in terms of our typical approach to solving problems, we would think about, well, let's try the possibilities, right? There's only n queens, and n, if it's 8 even, that's not so bad, right? Let's just try all the possibilities. There's n queens, there's n dot n squares on the board. That's not so bad. That's 64 for n equals 8, and there's just 8 queens. Let's just try them all out. The way that works in terms of the numerative space there, though, it's actually kind of painful. There's n squared possibilities. We could create a data structure called like queen position or something that would store the row and the column information for each queen we'd like to place. We then have an array n's of size n of those structures that would allow us to set the values of those row and column informations. Assuming that 2 queens can't share the same square, that they can share the same square, you could write a loop that just generates all the possibilities for those n queens. N squared spots for n independently placed queens. That's n squared to the nth power enumerations. Not so bad. Well, exponential math grows very fast. It grows exponentially. When n equals 8, what is n squared to the nth power? I don't know. It's really big. That's 64 to the 8th power, or 281 trillion possibilities that we'd have to enumerate. You know, a modern computer would get to it eventually. Replit would give up well before it got to that many number of iterations on our for loop. So I would argue it's valid. Like we talked about, there's always an iterative or enumerative solution for these kind of recursive approaches we are learning. But now here, at least with that kind of naive iterative solution, technically it works, but that's for n equals 8. Well, what if I want n equals 9 or 10 or n equals 100? We have a real problem there. We really can't go through that entire space. In reality, though, that's overstating it somewhat. I talk about how you could design a structure that stores both the row and column information for each queen, and I still think, like, naturally as a programmer, that makes some sense. But we can generally assume, just as we were trying to kind of manually figure out for the n equals 4 case, that there's just going to be 1 queen per column. Of course, we can't have 2 queens in the same column. I think that's obvious, right? Because then they would be in attacking or in check of each other. So you really don't actually need to store column information. You can assume that there's 1 queen per column. Consequently, there's a queen in this column, a queen in this column, et cetera, for all n of our columns. And that's just not just like saving in terms of bytes of storage. That's also saving in terms of the enumeration space as well. It's really not n squared spots you're kind of trying to consider for each queen. It's n different queen for which we're trying to independently determine which of the n rows that they're on, because we know there's going to be 1 queen in every column at the end of the day. So that does cut down quite a bit. From n squared to the n, it just becomes n to the n, which is probably fine if, potentially a little bit slow here for n equals 8. And even if you argue that that solution is sufficient for n equals 8, at least in the abstract, n greater than 8, which doesn't correspond to a real world chessboard, is equally interesting. And then that approach also does not scale in terms of how big of an n you could feasibly expect to implement using an iterative solution there. There's one such solution for n equals 8. Take my word for it, or take a minute and review it and convince yourself that none of those queens are attacking any of those other queens. I had it as an in-class exercise to develop the enumerative solution. It's actually a little tricky, and it doesn't lead to a good performance, a solution that we can actually get to the result to finish by the time we are done. But some of the data structures and functions we may want to write, I think can be applied towards the backtracking solution. We're going to want to have some data structure to represent each queen. We're going to have probably just an array to represent the solution, so an array of n of those queen structures to represent the solution. We're going to have a pretty complicated set of nested for loops to determine the solution space. We are going to have a function that basically determines, are we good? Are we safe, right? Is this queen in a valid position or not? And we'll still have to write that function. And then to actually see something interesting, we'll have to have some sort of function that prints out the chessboard. Not nearly as nicely as the chess team is going to be doing, but something that prints out something so that we know, we have a valid solution. Except for point 3 of enumerating the solution space, we need all those things for the recursive backtracking solution as well. And let's talk about that, what that would look like in practice. Again, a backtracking solution is a recursive solution in which we try to build up partial progress towards the solution. It is a little bit different than the Matryoshka doll view of recursion, in which we take a big problem and then recursively make it into smaller and smaller and smaller problems as we go. It's not that different, but in some sense, it's a slightly different mental model. In this case, we're kind of starting with the small solution and working our way towards successively larger and larger solutions via a recursive manner here. So the idea being, for solving the n queens problem, we first try to solve the problem of placing 1 queen. Then recursively take that first queen and try to solve the problem for 2 queens, and 3 queens, and 4 queens, all the way up into our number of queens is equal to n here. Kind of like what we were doing when we were scribbling it on the slide for n equals 4. As opposed to trying to solve it all at once, place 1. Once you've placed 1, see if you can place a second. Once you've placed a second, see if you can place a third. If you can't, we then have to go backwards. But if we can, we keep going forwards, and if we've gotten all the way done, if we've placed the nth queen, well, then we have at least one particular solution here. Here's just a couple, what I would call old school websites to try to do it yourself manually, as well as to kind of see the solutions in practice. I say old school websites because people don't make websites like this anymore. Nowadays, this would probably be a $3.99 iPhone app that you'd have to download to do the 8 chess queen solution. It doesn't zoom in especially well, but it'll work for our purposes here. We could implement this backtracking solution manually. It would be very time intensive to get to a final solution. But again, the idea is, as opposed to trying to place all n or all 8 at once, we start by placing 1, and we would have a function that would determine that, yes, that's a valid placement. We know there's 1 queen per column. We would then recursively basically call the same function again and say, now place the second queen. Wouldn't be able to place here. In fact, it won't let me click it. Wouldn't be able to place here. It won't let me click it. We would be able to place here. Recursively extend that solution to the next one. No good, no good, no good, no good. This isn't going to work just like it didn't work for the n equals 4 case, etc. as we make our way down. And then right at this point, I believe we're almost out of luck. We're getting there. Are we good? No. Able to place 7 of those queens, not 8 of those queens. We'd have to roll our way back until we have a solution that works. Here's a website, and you know it's old school because it's got like a traveling moose walking across the page. And they don't make websites like this anymore. That allows you also to manually do it, but also kind of shows visually how that backtracking solution would look in practice. That's slow speed, but it's doing the same thing I was trying to do with the mouse clicks here. Let's speed it up a little bit. Where it's going to try those placements, and each of those will be effectively a recursive call, and it will continue to do so until it can no longer generate a solution, in which case it'll return. It'll say, go back to the previous queen. And unfortunately, in this case, it's going to have to do a lot of backtracking, because I'm pretty sure, just like for the n equals 4 case, if you have a queen in that upper left space, it's never going to be able to find a solution. Speed it up a little bit. Hopefully it will find a solution. Don't actually know if it's going to stop or if it's going to keep going, but eventually that number will update from number of solutions found 0 to something non-zero. It's going to have to get that second queen all the way down. Questions about this before we jump into trying to implement it ourselves?
Do we have to implement those?
I think we should, but that's only if time allows. It's getting there. Again, for this backtracking solution, oh, it did find one with the, it did find one. Okay, so there is a solution, and I wish I could have rolled back. We're going to try to find the same exact solution and really answer the question in general, how many solutions are there for an n queens problem of size n equals whatever we choose. Get away from the poor moose here. So let's give it a try. We're going to start with the data structure to hold the solution. I think an array of just row/column information is going to be sufficient for that. We're going to need to have that function that determines, are we in a place that is valid or not, essentially. So given a certain queen, is another queen attacking that current queen location? We need a way to do the actual backtracking part, and that's where the recursion is going to make that relatively straightforward for us, which is we've tried a solution, it's no longer good, we cannot place the third queen, we have to go back to the second queen. By just returning from a recursive function call, we will essentially see that we are effectively going to be there, and we probably need to have some way to visualize the results to show that we have a working placement at the end of the day. This is an attempt to kind of visualize, again, for the n equals 4, what that backtracking winds up looking like. I think that animated website was also attempting to do it, but in terms of the data flow or the program flow of the resulting program, we start with no placement. We would try to place a queen. Perhaps we place it in this position. After having placed a queen in that first column, we would then attempt to iterate through the possibilities for placing a second queen. This is doing it one per row versus one per column, but it's the same exact concept, just rotated 90 degrees. That first placement would be invalid, we would move on. Second placement would be valid, we would move on. That third placement would then be valid, we would then recursively attempt to place the third queen, giving us all invalid possibilities. We would then go back, attempt to place a second queen again in that next location, attempt to then place the fourth queen, finally getting to a solution that's actually valid or not, depending on what our initial placement is. So we go column, this one does it row by row, but we go column by column. We attempt to check to see if a single queen is valid or not. If so, continue. If not, go back, go try the next queen along the way. With recursion, it's going to look a little bit different than our Fibonacci and our GCD and even our palindrome examples, because it's not going to be as simple as function calls function calls function calls function, but each depth of this kind of tree is going to essentially correspond to a depth of our recursive calls. It'll be the attempt of solve n queens or place queen, whatever you want to call that function, to place the first queen. Then an attempt to place the second queen will be a recursive call. Then potentially multiple recursive calls to place the third one, etc., for the next one, all the way through. That is still enumerative in one sense, but it's not as kind of naively enumerative in the sense that we just try every single possibility and just check to see if they work or not. We start from a working solution for some value less than n. We just try to extend it to the next value of n. We're only trying n things at any given level in our recursion. For that reason, it should be much more efficient to be able to find all the possible examples or values that we have here. We can give it a try. Whether we can successfully do it or not, I say here, it's advanced stuff, but we can try it. With your help, I think we can do it. Actually, printing out a nice chessboard is sometimes the hardest part about it. So we will just try to print, this is still going, so we'll close out of the moose. We can try to print it a much more basic kind of chessboard. So start with, we need a data structure to hold the information for a given piece on the board. What do we want to call it? That's good typing. Type def struct. Giving up naming rights. I don't know. Well, for an individual queen, We'll just store that information there. So we need a row. You know, as I mentioned, it's actually debatable whether we need the column information at all. But we'll have it. We'll just store it, and if we don't use it, that's fine. That's a structure to store a single queen, or structure to store a single queen. We are then hoping to solve, you know, the n queens problem. So at some point, whether it's a user input and we do dynamic memory allocation, or whether it's just a pound define and it's static, we're aware of those issues. I don't necessarily care about those issues today. Let's solve it for n equals 8. We could start with n equals 4, but I don't think the code is any different whatsoever if we write this properly. So then we would have to have the actual board itself. So board would be the right name for it. That board then would be an array of those, and just n of them, right? A board is technically n squared spaces, but in terms of what we're storing that's unique to a solution, it's just really the position of the n queens. So we are literally storing n queens as our board here to solve the n queens problem. We also, I mean, until we get a good function to print things out, we may want to say, you know, here's our solution count of here's how many solutions we found, and then maybe eventually we print them out once we kind of figure out what we have here. So we have main. We'll get to main in a second. To start with, we need to have a function to determine if a queen is in a valid position, and then we need like the main recursive call as well, right? The main function that lets us figure out for the ith queen, is it valid? Then check for the I plus 1 kind of queen here. We could call that a lot of different things because it really depends on the perspective of how you're calling it. We can call that a lot of things. It could just call it like solve n queens is fine. I mean, that's fine. That's what it's doing. It's, you know, solve the n queens problem. You could also call it like place ith queen or something like that, because that's also, it's really serving both of those purposes. This whole application is solve n queens, but we can also call this function here, and as we assume the column information is going to kind of be given, we can kind of just go either row by row by row or column by column by column to determine how to do our placement. So that'll be the input. Which value of I are we solving the n queens problem for here? Whether we go row by row or column by column doesn't really matter. It's the exact same code. It's a you know, symmetrical square thing, so it doesn't really matter how we want to do this here. And then in terms of all main's job would have to be, main's job would be just kickstart the solution, start with placing the 0th entry or the first entry, depending on how you want to think about it. And that's it. That's all main would have to do. Maybe we'd have main like, you know, print out found a total of this many solutions or something like that. It can do that. That's fine. But otherwise, main doesn't have much task here. It just kicks off the recursive call. And really, this is the whole function that's doing everything, is solving our n queens for us here. Here's the important part, right? We now have to determine sort of a hybrid of an iterative solution and our recursive solution here. For the current row we are on, can we place a queen? Can we place a queen at a given location? We should, if we go back to, you know, either this version or the Moose version, we should effectively try them all. Row equals 0 through row equals n minus 1, or column equals 0. I guess we're doing it column by column here this way. Can we place a queen at a given location? So we need some sort of way to look through all the possible columns. So for all of our possible columns, the question we have to ask, and we should probably, I think it'll be easier if we write a separate function to check this, but is row comma column a valid place to place a queen, to put a queen. So we're going to need some function that's going to check that for us. If for the input row we're looking to solve for, starting at 0, for the given column, which is going to be all the possible values of our column information, is that a valid place to put a queen or not? We'll want to write a function to do that. It, is valid is something we've used a million times, but is valid queen place? If it is, then we have to figure out what we want to do. So this is going to be kind of hard to scaffold up because we have to kind of write that function first. If it's valid, then what would I say? We can add the comments at least first. If so, if yes, then place the queen there. That part we can do. We're updating our board of row, and we really don't need the column information at all then at that point, or we don't need the row information at all, but board of row.column. We don't need the row information at all, but let's store it anyway. I did this exactly the backwards way I said I was going to do it before we started, but let's look at the job done. If that is a valid place to put it, let's update our board accordingly. Are we done? How will we know when we're done? Well, when we've placed the last queen, right? When our current row is our last value. Right now, I eventually want to print the board to make it look nicer, but I don't want to write that function yet. Instead, we can update our solution count. We have found an additional solution. If we're not done yet, we got to keep going, right? We now want to do the recursive case. Keep going and solve n queens with row plus 1. We have placed something valid in the current row. We're going to try all the columns. For a current row, we're going to try every single possible column to place it. If it was valid, and again, this function doesn't exist yet. We have to actually write this function. But if it is valid, store it in our global array here of this is where we've placed a piece, and keep going, unless we're done, but otherwise just keep going. So we do need a function that helps us to determine, are we at a valid placement or not? And that function was called valid place, and that needs to return some integer or Boolean kind of value, right? Because we need to know, is the piece in a valid location? And this one is a little tricky, right? We can go back to a picture of our chessboard with the website, I guess, right here. As I go to place that particular queen at that location here, I think, based on how we wrote this, we can assume there's not going to be anything in one direction or the other. This one we were doing it column by column. Now we're doing it row by row. We can assume there's nothing in the current row. We could still check, but there should not be anything in the current row. We have to check if anything else is in our current column. And what else do we have to check then? Diagonals. And diagonals are a little tricky. I don't have a good answer for what's the best way to do diagonals other than let's just try to kind of think about it a little bit, right? Let's assume this is called with row equals 4 and column equals 5, just to give an arbitrary example, right? Queens or pieces that would be attacking this piece would be all the stuff that's in the same column, right? So we're starting at 0, 0, 5, or 1, 5, or 2, 5, etc. Right? I don't think we have to enumerate them all, but we don't have to go up to the current row that we're currently on. We're trying to place something at that row. Those would be attacking because they all share same column. Anything in the same row would also be attacking. I don't think that's going to be an issue, but we have to watch out for that, I guess. We can also check it. And then what would be an example of a couple locations that would be diagonal from this piece? If we are at 3, 4, It's a little hard to see. I don't know if having this like grid open is an easier way to do it. Let's clear it. And again, starting at 0, 0, 1, 2, 3, 0, 1, 2, 3, 4. What would be some values of pieces that would be checking 3, 4? I asked the question. I should have taken your word for it. Yes, 4, 3 would be checking it. What else? Any others? That is, it's not going to let me click it. 4, 3. What else? I keep clicking the wrong thing. What would this one be? Thank you. 6, 1. Thank you. That's the one diagonal. Again, we don't have to go, well, if we're doing row by row versus column by column, and I keep getting it backwards, we also have to look at, what's this one then? That's 2, 3, 1, 2, 0, 1. And there's potentially others as well, right? There's also 2, 5. All the ones that are on diagonal, what do those have in common? Is there any mathematical expression? It's a little subtle to determine whether something is on the same diagonal. And it should all get a slope of 1. In fact, you're right. Slope is 1, or if we're being truthful here, precise. Absolute value of slope is 1, right? Absolutely. Rise over run. What is that equal to? That's equal. Well, we can do it either way, but that's like the column in the current piece minus the one that's currently being stored in the board at that location. And then divided by, same for the row, is equal to 1. If it's going to be equal to 1, we can do the division. We also just said if they're equal to each other, right? Then when they divide, they'd be equal to 1. So actually, yeah, so for any current piece, does the value of the row in the column, is the absolute value of that the same? Or the difference between the current placed row and column, is it the same as the one in our current location? We have to look at every piece that hasn't been placed yet. Or that has already been placed. So for all the previous ones up to this. So we're doing it row by row. So for row 0, 1, 2, and 3, has there already been a piece? And maybe since I've already messed that up twice, let's make a comment on that as well. Check rows, 0, ... row minus 1. Those are the only ones that have been placed so far. If the piece placed at that location is the same in my column, am I in my current column? Well, let's get out of here. Invalid. There's something already on the current column I'm at, that's not a valid placement. Otherwise, yeah, we do have to kind of do that if, I don't remember where absolute value is defined. We'll find it. If the absolute value of the board of I dot column minus column is equal to the absolute value of board of I dot row minus row, return 0. Probably standard lib. I don't remember. Seems happy. If it gets through every other piece that's previously been placed, neither of them are in the current column, neither of them are diagonal to the current one, then we're good. Then it's a valid potential placement. Feel like that was too easy, and the odds of this actually working are quite low. let's look at it one more time before I assume this. So we're not printing the board yet, so it's not going to look especially impressive. It's just going to print out a number. Try every possibility. If we're valid, place it. Of course, if we're done, be done. Otherwise, solve n queens for the next one. That doesn't stop. It just says increment a solution count and now place a piece at the next column to see if that's also the start of a valid solution. Otherwise, continue on and solve for the next possible row. We start by kicking it off for solving it for the first row. See what happens. 92 solutions, which I think that's correct, but I definitely know this should return 2. Okay. Let's print the board. It doesn't look very satisfying, if that's the case. Chess team, help me print the board. Okay, no curses. No, thank you. No cursing, no cursive. Let's print out specifically which solution we're on here. So let's print that solution count. And then if we're going to do that, let's not increment it here. So print board will also update the solution count. It's a chessboard, so it's like A through H, in like column headers. So, well, this won't work when n gets terribly large, but we can get it for a reasonable amount of characters. Print out, let's space it out. Let's print out the next letter. It's maybe taking you back to like week 2 in the lab. But so print out the letter A, then B, then C, then D with a little bit of space. And then do it again for each row. Print off the row number. Nope. It's a chessboard. 8 is the top and 1 is the bottom. So n minus I plus 1, right? A1 is the lower left corner. Well, it doesn't matter. Who cares? We can just print a number. It doesn't really matter what we're printing for those column headers. Print out the start of the row. And then print out the actual row. And here we actually have to check, like, if board of I, because we're doing it row by row, dot column equals J. So if we have something at that current location, and let's gap it out a little bit. And let's not do a Unicode symbol. Those never print well. Let's instead just print a queen or just an empty space like that one example was doing. Oh, so found a total of, which we know actually no longer really need to print out. And those are your 92 solutions. Why did that print out poorly? N 9 down to 2, n is equal to 8. 8 minus I. It's just to stop me from the simple errors. And well, those are your 92 solutions for the n queens problem for n equals 8. And there actually are quite a few solutions with the value in the upper left-hand corner there. I think, well, 92 is the right answer, so I'm sure that we did this reasonably close to correct. We can start to play with, okay, how big can we make n equal to and actually get a value? At some point, the actual printing of stuff may be slower than the solving process. And that console window itself is just very slow. You can never really tell if it's done or if it just gave up. 352 solutions for when n equals 9. Let's go crazy. N equals 20. Well, we need a little bit more space to print that. Need a little bit more space to print that. There we go. And we'll let that run here. Questions about n queens. Otherwise, we are done for today. Okay. This weekend is probably a big push on projects, going from like scattered code ideas to actual working stuff that you hopefully just kind of take the last week to kind of just improve and get the way you need to get. I have office hours today, so please feel free to stop by if there's somehow I can help. it's harder for me to help at this point because now I'm looking at hundreds of lines of code that you've written, and I don't necessarily know what your goals are, and I have to resist the temptation to like have you start over and things like that. But please feel free to stop by. Otherwise, Monday's our last week, so let's enjoy it. Okay. All right. Enjoy your weekend.